हाँ श्याम भाई, नमस्ते। बताइए। अच्छा, हो गया। सुमित,
हाँ सर।
वो दोनों ठीक हो गए?
हाँ, दोनों प्रेजेंटेशन ठीक है।
अच्छा, तो मैं उनको बोल दूं क्या क्या नाम है अपने मनसुखानी जी को?
हाँ हाँ, उनको भी बोलिए, बिल्कुल चेक करते हैं उनकी प्रेजेंटेशन।
ठीक है, मैं एक
सर
मिनट।
ऑर्डर एक बार ही ऐसा मेरे को लगता है कि महेश जी का फर्स्ट पहला कर लेते हैं, फॉलोड बाय अरुण सर एंड देन मनसुखानी जी, राइट?
यही तो है, और हमने क्या बताया तुम्हें?
ठीक है।
पहला महेश जी का है, महेश जी का 10 मिनट का है।
ठीक है, तो महेश जी का इंट्रोडक्शन आप करवाइएगा।
हाँ, इंट्रोडक्शन हम तीनों का करवा देंगे एक बार में ही, पहले ही में,
ठीक है ठीक है
जैसे पिछली बार ही किया था।
ठीक है।
जी 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 सर, जी सर, प्लीज प्लीज लागू। हाँ जी। सुमित,
बताइए।
मैंने तुम्हें ललित साहब का मोबाइल नंबर वो व्हाट्सअप कर दिया है।
किसका?
ललित मनसुखानी जी का
ठीक है।
व्हाट्सअप कर दिया है। तो वो लॉग इन कर रहे हैं, तो उनको होस्ट बना करके, होस्ट बना करके और उनका वो करवा के उनसे कोऑर्डिनेट कर दो जरा। और रेलवे एकेडमी का इंट्रोडक्शन तुम कराओगे सबसे पहले, देन यू विल हैंड ओवर टू मी।
ठीक है ठीक है। Lalit sir, good evening. I've made you co-host. Lalit sir, welcome. Good evening, Arun sir.
Good evening. Good evening. How are you?
Good sir. How are you, sir?
Thank you so much. How are you, all of you?
All well, sir.
नमस्ते अजय जी नमस्कार.
नमस्कार नमस्कार सर नमस्कार. मुझे अनम्यूट था, मैं इसलिए आपको नमस्कार मेरा पहुंचता नहीं. नाउ आई हैव अनम्यूटेड इट.
Mansukhani, good evening.
Good evening, sir.
Good evening. How are you?
Good evening, sir.
Good evening. Parvatika, thank you so much. How are you?
Fine, sir. I am fine, sir. How are you?
Thank you. Come take care of your health.
Yeah. Sure, sir.
Sir, I think Mansukhani sir had joined, but he's logged out now. So, Mahesh sir, I have your presentation. So,
Yes.
I can also upload it. There's no problem.
okay, right, sir. Sir, I'll start with after a brief introduction about Railway Academy, sir. Sir, I'll upload Mahesh Yadav sir's presentation. Once he finishes, then I'll start your presentation, followed by Mansukhani sir's presentation.
Okay.
So,
not many people are there.
sir, they will be joining, sir. Around 7, I think. Around 7, they'll start joining. So usually people start joining around 6:55 or so.
Okay.
सुमित, ये मनसुखानी सर का वो टेस्ट हो गया क्या?
नहीं सर, मनसुखानी सर लॉग इन किए थे, लेकिन उसके बाद लॉग आउट कर गए.
तुम जरा एक बार उनको फोन करके जरा बात कर लो कि उनको क्या प्रॉब्लम हो रही है, जरा समझ लो जरा एक बार प्लीज.
Good evening, Mansukhani. How are you? You are mute.
मनसुखानी सर का म्यूट है. हाँ, अब
Good evening, sir. Good evening, everybody, sir. Sir, let me just make a trial, sir. Try sharing, sir. I'll just get back, sir.
यादव जी क्या हाल चाल है?
गुड मॉर्निंग सर. गुड मॉर्निंग सर. ठीक है सर.
इवनिंग. क्या तबीयत ठीक है?
हाँ ठीक है सर, एकदम फिट है.
क्या हुआ तुम्हारा पंचायत का?
वो तो टाइम वो तो निकल गया.
निकल गया. चलो अगली बार करेंगे.
महेश जी, आपके चेहरे पे लाइट नहीं पड़ रही है. आपका चेहरा बहुत डार्क दिख रहा है. जरा थोड़ा बल्ब की तरफ बैठिए, so that your face is visible.
अभी आया. Yes,
अपने फेस पे लाइट आनी चाहिए. फेस पे.
हाँ, फेस पे थोड़ी लाइट आनी चाहिए.
And now it is okay.
Yes, now it's good. Now it's good.
गौतम साहब, आप क्या हाल, कहाँ हैं आजकल? How are you doing? Mr. Gautam, Arun Saxena here.
गौतम साहब म्यूट है सर. सुमित, तुम थोड़ी देर के लिए सबको खोल दो अभी 10-15 मिनट. हेलो सुमित.
ठीक है ऐसी ठीक है. Then there will be lot of noise.
नहीं सर, अभी तो इंट्रोडक्शन प्री वेबिनार जो है ना, मैंने कहा कि एक दूसरे को ग्रीट करने का काम हो जाए.
Microphones should remain in mute normally. Patel, Rajesh Patel, how are you? You are mute.
Yes, he is also mute. मैं बोलता हूँ मैं
not I unmute now. Yes sir. Very good evening sir.
Good evening. How are you?
It is really very good sir. It's nice topic and whole history we have taken, and now we are coming to the next page sir.
I do not know. Mr. Parvatikar was very persuasive, and he was wanting me to do something. So whatever I could make out from my old documents or my own remembrance, I've tried to present the paper in a manner so that actually the kind of questions which have come, it indicated that there's a wide variation in the kind of people who are joining the webinar.
Correct.
Therefore, it is important that
exactly sir.
They should be adequately covered so that the subject is rather clear. And therefore, I expect a lot of questions at the end, because at the end of the webinar, you will be all confused.
No, it is really, sir, you are the right person for this one, because you have seen the TPWS earlier also, ACD also, and now TCAS also. So whole change in railway system, particularly signaling, you are the person who has seen from the basics.
And that is okay, I think, but the real creator of the concept today is Mr. Mansukhani. You can see
correct, yeah.
With the Prime Minister, you can see him there on the screen.
Correct.
He has done this Indian Railway Train Control System, which is a totally Atmanirbhar Bharat. The focus is on Atmanirbhar Bharat.
Exactly, sir.
In the last 15-20 years, we have seen a lot of different systems, right from the Russian system to the American system, to the Japanese, to the European, and the British system, definitely. So I think ultimately we realize that what India needs is something different.
Correct.
And what Lalit Mansukhani has been. In fact,
yes, Lalit has brought flavor of this designing, sir. Designing things from that one. He has taken quite good. The pickup he has started, and he get the things really.
So, Mr. Kanu, you can start only when the number of participants are 50, or you can start early.
सर हो जाएंगे 50 तो हो जाएंगे स्टार्ट करते करते. नो प्रॉब्लम. अभी तो 15 हो गए हैं. पीपल आर ज्वाइनिंग. सुमित, ये हो गया ललित जी का प्रॉपर?
सर वो मुझे गाइड तो कर रहे हैं, लेकिन मेरी स्लाइड मूव नहीं हो रही है मेरे यहाँ से. हालांकि स्पीड वगैरह सब प्रॉपर है.
अच्छा.
और सब कुछ ठीक है, बट समहाउ कवर स्लाइड आने के बाद स्लाइड मूव नहीं कर रही है. मैं स्लाइड चलाता हूँ तो एक बार और मैं ट्राई करता हूँ स्टॉप शेयरिंग करके.
नहीं हो तो सर आप इसको एक बार भेज दीजिएगा, तो ये अपने यहाँ से
मैं तुरंत भेजता हूँ.
हाँ ट्राई करके फिर खत्म कर देगा.
सर आप मुझे मेल कर दीजिए. मैं आप आपके पास मेरा ईमेल आईडी है क्या सर? मैं अभी आपको एसएमएस कर देता हूँ अपना ईमेल आईडी.
हाँ 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 हाँ. ओके, थैंक यू.
Lalit, very good evening.
हाँ, गुड इवनिंग राजेश. जस्ट मैं पहले ये कंप्लीट कर लूँ सो दैट
बिल्कुल
टाइम बच जाए.
यस यस.
Lalit sir, I've just SMSed my email ID to you, sir. Kindly send me the presentation.
हाँ, गॉट इट. मैंने आपको व्हाट्सएप पे भी किया है जस्ट अभी.
Done, sir. Done.
Mr. Tan, you are from which place? Mr. Tan? Mr. Nathaniel Tan?
Sir, he's from Singapore.
Okay, okay. So Holu is from which place? Holu.
Dole. I think Dhok. Yes, you can unmute yourself and actually just give us a brief introduction about yourself. So Tan and Yogesh, Dhok, if you could.
Holu.
Low, yes, Holu.
I think they are not able to hear.
Mr. Huang has come now.
सर इनको चैट करके मैसेज डाल देता हूँ.
Hello. Hello. हाँ बिल्कुल बिल्कुल बिल्कुल. आप भेजिए सर, मैं व्हाट्सएप पे कर लूँगा. आप भेज दीजिए. जी सर. डन सर, डन. मैं कर दूंगा. आप भेजिए. हाँ सर, वो ज़्यादा बेटर है. कुछ ज़्यादा चेंज. हाँ, डन. आप गाइड कर दीजिएगा, मैं उसी के हिसाब से रन कर दूंगा. डन सर. राइट.
अरुण सर, आप चैट में आ जाइए. I have given the message in the chat, so people are introducing themselves in the chat.
Okay.
Sir, we'll wait for 1 more minute. Participants are just joining, so we'll just start it in next 1 minute.
Welcome, sir. Mukul Verma sir. Welcome.
सुमित अपना प्रेजेंटेशन शुरू करो.
मैं 1 मिनट जरा इसको. एक सेकंड.
Good evening, sir. Basu sir, good evening. Arun Saxena here. Good evening, sir.
सर वो म्यूट है इसलिए आवाज नहीं आएगी आपकी उनकी आपके पास.
Good evening, Mukul ji. Dr. Mukul Verma. How are you? Very senior stalwarts from the Indian Railways, Dr. Mukul Verma and Sujit Basu is almost an expert on, he was the initiator of the automatic train protection systems right in the beginning in the Delhi, Kolkata Metro.
Right.
Long back. Great expert.
Sumit.
Yes, sir. Okay. So,
this is not your presentation.
Good evening, everyone. My name is Sumit, and on behalf of Railway Academy, I welcome everyone. I welcome everyone to the second session on TPWS. Last week, due to technical issues, we could not complete the session. Hence, today we will cover the remaining sessions from last week's presentation. So today we have our three eminent guest experts, Mr. Arun Saxena, Mr. Lalit Mansukhani, and Mr. Mahesh Yadav with us to share valuable insights on TPWS. Before we start, I would like to share a brief introduction about our organization, Railway Academy. We started our training solutions in 2017 with two of the eminent universities in India, Rajat Bhara University and MS Ramaiah Universities, where we launched India's first postgraduate diploma in railway signaling and telecommunications. Since then, Railway Academy has been launching many online courses to help working professionals in railway industry attain new skills needed for new age railways. With this a brief introduction, I would like to invite my colleague, Mr. Ajay Singh, to briefly introduce our eminent speakers. Over to you, Ajay sir.
Good evening, everybody.
Sir, you're audible, sir. You can continue.
Actually, मेरा कुछ सिस्टम में प्रॉब्लम आ गया. Just a moment. I don't know what happened. So there is a problem in my system.
So please continue with your speech. We can hear you.
Good evening, everybody. I'm Ajay Singh. I'm pleased to introduce my guest speakers today, who are who are the experts in the TPWS. First speaker is Mr. Mahesh Yadav. He is from the Western Railway, and he's an IRSC officer of 208 batch, having 40 years experience in various aspects of the systems. The second speaker is Mr. Arun Saxena. He is very, very eminent person, retired as a general manager from the North Central Railway, and he has worked in many aspects of the communication systems of Indian Railway. He is also he's a IRC officer of 1978 batch. The third speaker is Mr. Lalit Mansukhani ji. He is a 1991 batch IRC officer. He has basically he's the initiator of many aspects of the this kind of control system, and he's to his credit there are so many awards and rewards he has already received. So I would like to invite Mr. Mahesh Yadav first to start his presentation, please.
Thank you, Mr. Ajay. Good evening, everyone. Thank you, Mr. Parvatikar, to give me opportunity for this webinar. Ajay, you are hearing me?
Yes, sir.
Hello? Yes. So, this today's topic is tail protection warning system. The last week was also there. So, due to some technical problem, I could not join at time. So, regarding this tail protection and warning system, how this in brief I will tell, and further in detail by Saxena ji, you know very well. Last time we had also detailed about the system and what is the TPWS and what is the system in the advancement in this field of tail control and alarms. So what is the to go first the limitations of the so this limitations of convention, the driver doesn't know what the
Voice is this is not
yes. Hello, please share by this Mr. Ajay, please share by this PPT.
shared. The PPT is shared, sir. Whenever you
Yes,
want to move to the next slide, please let me know. I'll share.
So go for this first slide. There are limitations of the conventional signaling. So in conventional signaling, what are the limitations? Basically, this conventional signaling has so many limitations. Regardless, this driver doesn't know how this what signal is going to have to further in advance. What signal is has to go, which speed has to go, which distance has to go, and what is the gradient of the signal here. So, and the visibility also depends on the fog or this weather, what is the rain or fog. So the visibility also there. So limitations in the for the drivers also. So all control in the conventional signaling on the drivers and this on the seeing the signals. And also this in the conventional signaling, the driver's mistake, there is no control on the driver's mistake. Yes, drivers passed the signal, particularly the passage at the signal at danger. This is the main cause of this accident in the conventional signaling. And also in conventional, higher margin of speed and distance to be kept. In the two trains, there is a headways to be more, so to have a safety. And also in conventional signaling, the safety is less and headway we cannot use this line capacity in full way. So this is the limitations of the our conventional signaling. So in 19th, it was think that some systems should be introduced. So first the AWS system was introduced. So AWS system was introduced in particular in India in suburban of our Mumbai suburban. So the basic system of this tail protection system is AWS. So automatic warning system, this was a system was introduced to have a when driver approach the red going to signal if in signal in advance is a red, then it gives a alarm to the driver. If the driver ignores the alarm, then he can pass that. So this was also not a foolproof system. So further the tail protection systems was introduced. Now this system It is a particularly due to this gradual increase in numbers of, you know very well, the gradual signals in past danger of the signal pass in recent years. So many severe accident was occurred, particularly this Guy Sir and Faruzava. So many accident was occurred, and it was think that by the various committee, the train protection system should be introduced in the India Railway to protect this. Also, in the automatic block system, there was a limitation during this fog season. There is a limitations of the train. So that this system was firstly introduced in this Agra, Jhansi, and further by Agra and Delhi and Delhi, Agra, Jhansi, and Delhi and Mughalsarai sections. So the TPWS was introduced by to avoid the signal passed at danger by the drivers to ensure safety, and this system is also initially effective solution can be introduced 10% of full ATP. No doubt this ATP is a further advancement and full protection is there, but this system TPWS initially introduced at the low cost. In details, the Saxena sir will tell about the all the things, what is the further in detail about this. So what TPWS does it, TPWS does it reduce to the speed in the train approaching the stop signal. If driver fail to get the speed, train will control under the control how the stop of the signals. So this onboard system of the TPWS will act when driver goes beyond the this targeted speed by the system is advised. What are the benefits of the drivers? The driver machine interface on the board on board will show all the conditions. Driver will know what is the permitted speed, what is the actual speed is running, what is the target speed, what is the targeted distance, level of operations, and mode of operations, and all things, all the this alarms and all the while visual and with this audio warnings are available on the onboard. So in emergency, in service emergency brakes also indicate all things are on the board. Drivers know about that this TPWS system is working on the route. So in a brief, I will tell about this TPWS and further detailed by Saxena sir. So in TPWS system, we have a system as a whenever the train will go at the 20 to 400 meters beyond before this stop next stop signal, the first alarming loop is there. If we will pass the alarming loop, then all the alarms will come. That further signal is red. And after a 44 to 36 meters, there is a trigger loop, and whenever we will pass the engine by the trigger loop, trigger will start and regulate the system on the.
Mahesh sir, am I on
Yes.
the right slide, sir? Please.
Please rotate the slides. Go for the slide number 7.
Slide number. So is this the slide, sir?
7 number. Slide number 7.
Slide number.
Go to the slide number 7.
So this is 7.
The diagram is there.
Yes, sir. This is 7. Sir, are you not able to see the slides?
I'm not able. What is true? I'm able to see
the slide. Are you able to see the slides? Please type in yes in the chat.
No. I'm not ready.
Participants, are you able to see the slides? Please. Okay. Sir, please continue. Participants are able to see the slide.
So there is a 3 loops are there in this alarming loop, trigger loop, and final when if still if going that the automatic train will stop by the this breaking of the signal at the targeted before the stop signal. So this is the brief of this purpose of this signal, this TPWS, and this TPWS is a ERTMS level 1. The 2 and further the advancement level 2, 3 are there now. 3 also is to come in detail. Why our experts will tell. So the main components of ERTMS, European Rail Train Management System, control system, ETCS, European Train Control System, and second is ESMR. So there, whenever system will introduce, so two systems there now. Level 2 is most of the there now. Level 2 is there. So in further, I will tell to Sri Saxena sir to go for the all the system. But before that, he involved in this system OECD and involved as a member of expert committees in the Ministry of Railway also. So he can more or better can tell it was also detailed by him. So further I will tell to Saxena sir, please go ahead, Chris. For any query for me, anybody can ask about me, but further any question will be raised by the end of this session.
We'll take up
Thank you, sir.
At the end. Thank you, sir. Thank you, Mahesh, sir. Thank you so much. We'll take up questions at the end of the session. So I'll invite Mr. Arun Saxena to take up his presentation. Welcome, sir.
Thank you, Mr. Kanu. Can you give me the sharing possibilities?
So sharing, sir, you can let me know. I'll move the slides.
Okay, that will be more inconvenient, I think.
Okay, sir. Sir, if you can, sir, you can share your the presentation at your end. I'll give you sharing rights, right? Sir, you already have it. Please share it.
You can withdraw your presentation.
Yes, sir. I've withdrawn. It's done, please. Yes, sir. Visible.
Yeah. So good evening to all of you. Let me first of all thank my very senior Mr. Basu, who is on the list of participants. I could see him. Dr. M.R. Verma, he also is an expert on electronic signaling, and he is also in the group. I in the presence of these seniors, I think my job has become more difficult, and therefore I would like to I would like to request them to make critical comments on wherever I am going wrong. Thank you so much, Mr. Ajay Singh, Mr. Parvatikar, the entire team of people here available, and the focus of the entire talk when I was advised about this webinar was train protection warning system. Now, I believe that before you talk about train protection warning system, you must first of all understand what the systems are, in the current systems are, the conventional systems are, and how trains are being run today. And therefore, enforcing the signal aspect and the movement authority becomes a requirement. But the moment we go in for conventional signaling systems, we find that there are some gaps in the system, which I'll talk about later. These gaps have to be plugged so that the system becomes largely automated, and we are able to prevent the cases of signal passing at danger. We are able to enforce speeds, including the temporary and permanent speed restrictions, and we can also prevent collisions. So briefly, the webinar will cover as railway signaling and train control system, which existed in the last almost more than 6 decades. And where are they required? What are the functions? Why are they required? How signaling really grew in this country, and what was the impact? I will have one slide on that. How it really affected. I hope I'm audible. You can hear me.
Absolutely perfectly, sir.
Okay. So how signaling grew in India, and what was the impact, especially on the safety front. Then the basic concepts and functions of line side signaling. Then we go into the area of automatic train protection systems, how they evolved. The first trials, which I think many of us didn't know that it was done in way back in the British India. And then we go to the conventional signaling, to the state-of-the-art universal interoperable systems. And then we go to the indigenous ATP, for which I've requested Mr. Lalit Mansukhani, who is the architect of the indigenous ATP, which is now called Indian Railway Train Control System, which some of us call as Train Collision Avoidance Systems. But that is not the end. And in the end, I would request that this area is an evolving area, continuous area, and different systems are available world over. Therefore, it's important to learn the interfaces, the design of the various systems, how they are conceived. And this webinar cannot cover all these aspects of design, engineering, integration, field installation, testing, commissioning, simulation, and all. And therefore, I would request participants, whoever is interested, that are we required to organize a specific webinar on a specific subject. For example, it could be ETCS level 1 or level 2, or even the Indian Railway Train Control System. You can specify your requirements, and then we can have resource persons and subject matter experts tied up in a manner to really focus on that. Each of the courses, ETCS level 1 requires almost 20 hours. ETCS level 2 requires slightly more. And Indian Railway Train Control System also requires around 20 hours. So therefore, I would request the participants to kindly. Now, let us come to this slide, which is for the need for railway train control system. You can have a look at this, picture on the right-hand side, and you can see the entire traffic on the road is totally, that is in a state of jam, I'll say. But all the passengers in all those vehicles can go into one train. And you can see on the other side, the entire track is lying vacant. And that precisely is the issue, that we need to maximally utilize the system. And that is the area in which signaling comes into picture. And as all of us know, that the trains run on fixed rails and cannot change their path by steering away, unlike the road vehicles. Trains also have very higher speeds, much higher speeds. They are running at closer headway, especially in automatic signaling territories and ETCS level 2 sections. They have got heavy trailing loads, and therefore they require larger braking distance drop. And for that reason only, that they are required to be informed about the conditions of the section ahead. And that is very necessary, so that the train is able to be steered in a manner that it passes the next speed restriction in the required speed, or if it required to stop, it is able to stop short of the obstruction or the red signal. So now we specifically focusing on the functions of railway signaling train control systems. As I mentioned, that primarily the focus was initially on safety only initially. And therefore, that is, we always remain paramount. Provision of high level of safety in train operation is paramount. The second thing, as the traffic started increasing on the system, we found that more and more trains are required to be run. And therefore, I will explain about certain techniques of improving line capacity. So we had trains started running at a close headway. And therefore, again, signaling comes into the picture for the reasons explained earlier, for reasons of safety. And as we move towards more complex operations and more number of trains in the same junction station or yard or major yard layout, we find that a lot of movements are required to be done parallelly, because that is the only productive and efficient way of train operation. And that again requires signaling, and that is achieved through our concept, which is called interlocking. As I think Mr. Yadav also mentioned about operations during foggy weather, and that was a big problem. We have seen that trains crawling right from Kanpur, maybe Allahabad to Delhi, and taking 11 to 24 hours extra. And that was just not acceptable. And therefore, there was a burning need to go in for an automatic in-cab train protection system. And one of the functions which I think most of us tend to ignore is the online monitoring of assets for passenger information, for train control and management, and for predictive maintenance for zero defect. And all these functions together are available in railway signaling and train control systems. And therefore, railway signaling has been classified as a symbol of trust. This symbol of trust is a word coined by one of my senior, who was a member electrical at that point of time. And he says that whenever a signal is green, I don't look at anything else. I know everything is all right. When the signal is green, everything is all right. I can run at the maximum permissible speed. And therefore, he always says, signaling is a symbol of trust. Now we come to the most vital aspect of safety in train operation, and that was the track circuit. Now you can imagine that if the track circuits were not there, how the trains would have been received. And therefore, initially at the station, we started doing track circuiting, then interlocking of points and signals to improve the safety in train operations, and also interlocking the level crossings and slots. And slots are basically, if you are trying to move into somebody else's area, some other cabins area, or some other control systems area, then you have to have a slot from that other controlling agency, and then only the signaling can be cleared. The second thing is this, how we achieve safety between the stations. And that initial concept of absolute block system of working was ensuring at all times only one train in the system of absolute block working. And that is ensured by block instruments of different kinds, so token to tokenless, and now block proving using axle counters, and many other concepts have now emerged. At level crossings also, we have been providing safety devices in terms of interlocking with signals and approach warning for the signals as well as for road users. The only thing which we gave to the driver in the last 50 years was the multiple aspect color light signals for improving visibility. That was a big relief to the loco pilots, driver and motormen, because the earlier system of semaphore signaling, especially within the night and then during foggy weather, it was very difficult for the trains to move, and they were used to literally lose speed, and in the process, the punctuality goes used to get lost. But multiple aspect color signals not only gave them improved visibility, they also gave them adequate distance. They also gave them adequate distance to brake. You will not be suddenly presented with a red. You will be getting a yellow, you will get double yellow and then green. The green, double yellow, yellow and red, in that order, if you get the signals, the driver was able to control, and you have got a full braking distance available as per the worst case freight train also, which has got a braking distance, if it is in loaded condition, about 1.7 to 1.8 kilometers. And finally, we come to the control centers, which improve the productivity and performance. In fact, I will give an example that even the centralized control has an impact on safety, which I will explain with an example of Meerthal accident, which was a head-on collision. And then we come to the last point, which we have been touching for the last, I think, 1 week, and that is onboard train protection systems. And this is the area in which Indian Railways, or for that matter, most of the world railways, will have to work on this system for the next almost 2 decades, so that you are able to prevent accidents. This is a typical signal interlocking diagram, and I think that most of us know about it. This is how the typical simplest of the diagrams. I just for indication purpose to the people who are not really aware of signaling plans. Now I will now focus on how the signaling grew and what was the impact. Now you can see from right from the year 2002 to 2017, there has been a substantial increase in almost every area, right from the multiple aspect color signals, which are now almost touching 6,000, which is 93% growth in the last almost 15 years. You can see electronic interlocking, 8,000%, unbelievable. Nowhere in the world the growth of electronic interlocking is of this order, 8,000%. Then you can look at block proving, that's almost 250% increase. LED signals for improved lighting and longer life. You can have, you can see 9,000%, more than 9,000%, sorry. And then we also did some work on intermediate block signaling and automatic block signaling for the purpose of line capacity. And you see the impact now. The impact is very, very obvious and clear. As you did the track circuiting, you improved your block proving, you started interlocking stations with centralized operation using either panel interlocking with relays or route relay interlocking for larger stations, or electronic interlocking, which is the convention today, and the interlocking of LC gates. The number of collisions and the number of accidents at level crossing gates came down. And if you just look at the figure of 1961, in the year 1961, we had 130 collisions. And luckily at that time, the media was not that active. If had the accident had taken place in the current years, it would have been a chaos for the railway board and the railway ministry to explain things. So from 130, because of these signaling inputs, we have come to almost 5. Now these 5 cases, many of them, or I'll say most of them, are on account of signal passing a danger. And these 5 collisions will have to be controlled. And that's why all this talk about automatic train protection systems. And later on, when the traffic grows further and further, you talk about line capacity using onboard train protection systems. Now we come to the typical initiatives which we have taken for line capacity. And this is a clear indication. In fact, if you look at the early, prior to 1940s, you will say that track circuiting also was an issue. If the track circuiting is not there, then the amount of time which the station master will take to receive a train was very, very high. And that definitely will eat into the line capacity. And therefore, apart from the safety which we discussed earlier. So track circuiting became a tool for improving the line capacity in the 1930s and 40s. Later on, in fact, in the initial years, we also till the 1950s and even 60s, we did not have interlocking at many stations. They were either non-interlocked or they were modified non-interlocked. And therefore, the interlocking had to be done. And there have been cases of accidents on account of interlocking not being available because many of the interlocking functions are disable many of the conflicting signals. And therefore, interlocking had to be done. Apart from improving safety, it also ensures flexible, simultaneous, and expeditious movements. And therefore, it again provides incremental line capacity. Now, in the block section, that is the main control of the line capacity. In fact, there's a
Hello. Saxena sir, your audio is not, you're not audible. Arun sir, your audio, you're not audible.
Now I'm audible?
Yes, sir, absolutely. Please go ahead.
Okay. So I was here that we were talking about how to improve line capacity by using tokenless block working. As you know that earlier systems were either using paper line clear or some kind of a wooden staff or a token. These methods were taking more time to be handed over to the driver because this was the only authority to proceed into the block section. Until the authority is received by the driver, he just cannot go into the block section. And therefore, the time taken to get the token from the block instruments became an issue. And this led to the loss of line capacity. And therefore, the signal engineers thought about the concept of tokenless block working handle type, which reduced this time taken for putting the token back into the system, obtaining a new token, and then giving the new token to the driver, except in case of run through where the driver was able to take the token in the running position. In all other cases, the token had to be extracted. And therefore, in single line section, this had become an issue of line capacity, and tokenless block working was introduced on a very large scale in the 60s, 70s, and even 1980s and 90s also. Later on, by the time at the end of 1990s, the concept of axle counter came in, and then we thought of having a block proving by axle counter using a block panel, which was totally has a feature of non-cooperative operation and which does all the requirements, meets all the requirements of the rules and the block manual, that the train has to be announced to the station in advance. The automatic fuel feature does that, and the train out of section also is automatic. So the entire system was again able to improve the line capacity further, because in the case of tokenless block instrument, you have to still operate the block instrument. Then multiple aspect signals, anyway, I expressed earlier that it has improved the running in the section because of the more visibility and the better visibility and adequate braking distance being available. The confidence of driver went up, and he was able to maintain higher speeds, including the maximum permissible speed. And the other impact effect of MACLS was that the driver had gained the confidence to run at the maximum speed allowed. Then came the centralized control traffic, which we initiated in the late 1960s, and we had got 3 control centers in this country in the 1967 to 1971. One on the Gorakhpur-Chhapra section of Northeastern Railway, one in the Guwahati Northeast Frontier Railway, and the third one was a totally indigenous make CTC designed by a signal engineer of Southern Railway in Chennai Egmore to Chingalpet. Other than this was a situation in the case of single line. Now, when you needed much more capacity beyond that, obviously doubling has to be done. And after doubling, line capacity also gets exhausted on account of block limitation. Then we went in for intermediate block signals, where we allowed the two trains to be put into the same section with the adequate protection of signals. And with further increase in line capacity was ensured by provision of automatic block signals, which reduced the head weight to almost 5 to 6 minutes on the main line. And especially on the Bombay suburban section, it was as low as 3 minutes, especially for a defined consist of train of 9 coaches or 12 coaches. This we have explained. So this we have explained already, just diagrams for the reference of the people. I have explained all these 4 of them. Now this is the complexity in the system. If you can look at this chart, you will find that this is a typical chart of the Ghaziabad Aligarh section, where you can say that line capacity is nobody's concern. Every hour we should be able to run at least 10 trains each way, but we are running hardly 3 or 4. And this is the situation because of a mixed traffic scenario, number 1, varying braking distances, and the system of manual operation. All this was largely covered in the centralized traffic control system, which was installed at Tunla. And with that, we found that instead of running 3 or 4 trains per hour, we are now running, I'm talking of each way, we are now running 6 to 7 and at times 8 trains each way per hour in each line. This we have discussed, I think, about line capacity, but this talks about how the automatic signaling is achieved using track circuits or axle counters. And this has been done in almost 2,500 kilometers, route kilometers in the country. And the situation continues. But with the advent of Indian Railway train control system, I believe that they have a feature of improving the headway. And the proven European train control system level 2, where you can also optimize line capacity. That is how it can be done. This is a typical diagram of a 4-aspect automatic signaling section, where you can see how as the train moves, you will find that ultimately from the green to green, you will find that you will have a distance of 3 kilometers, which is maintaining the required level of safety. Then we now come to the subject of train protection ones. Now, as you know that as we went on increasing the train density, we found that the driver has to negotiate a large number of signals while moving from station A to station B or from origin to the destination. And therefore, this was a very, very severe impact on his mental state. And this was some kind of a pressure on him, and that led to mistakes quite often. Although in the Indian in the Indian context, we have put on the mainline trains 2 drivers, and we believe that both the drivers will not fail on the same day, at the same place, at the same time, on the same train. And this was, if you work out the probability of this kind of a failure, wrong side failure, you will find that that is the reason that trains are still running in this country without collisions. There are occasional cases, there are very, very rare cases, I'll say, very rare cases. But even those rare cases have to be plugged, and therefore the system of automatic train protection system on the cab was initiated. And I think Mr. Yadav mentioned about how it was started. We'll further go into the details of that. This is a complete system which we envisage that this is the entire network should be like this on the Indian Railways. With the automatic signaling, train protection systems, TMS and CTC, mobile radio. This is the complete system which we envisage, which will give, if you take a holistic view like this, which was taken by the Railway Board in the project Modernized Train Control System or Modernized Signaling on Indian Railways. That project is now put on hold, but that project mentioned about this. Now I come to the word which I used the verb in the one of the previous slide, that the gap. There is a gap, and their gaps are of three kinds. One is the information exchange between the station and the controller. That means the signals and the controller, there is no contact today. And the controller is the person who gives commands, who authorizes the movements. And therefore, we had an accident, and the solution is the centralized traffic control. And the solution, and we had a situation in one of the accidents in the year 2004, when there was a head-on collision between at Meerthal station. The problem was that between the two stations, there was no communication, and both the station masters thought that they can dispatch the train without any further intervention by anybody. They did not talk to the central control, and in the process, both of them sent the train, and there was a collision. This collision would not have taken place had there been centralized traffic control in that area, right? Because the centralized traffic control would not have sent both the trains at the same time, and the system of interlocking would not have allowed it. The system of command sequencing, it will not allow it. Second gap is in the form of communication gap, that is between the loco pilot and the dispatcher. Again, the issue is that the controller is controller. He is the person who gives the command where to stop, where to go, where to run through and all. And the loco pilot is not in direct contact. He is in contact only with the nearest station master and the guard on the normal walkie-talkie sets, which we are called VHF sets. And this also can prevent cases of collisions on account of a derailment of another train, which is coming from the other direction, and the other one not getting information about it and goes and collides into that derailed wagons or derailed coaches of that train. This kind of a collision can also be prevented provided the time available is there. If the time available is not there, and this particular feature has been there in the GSMR system of communication, mobile train communication, where there is a SOS button. You can press the SOS button and all the trains converging into that area will get an emergency alarm, and they are advised to be stopped. We have in a device certain systems which are actuated by the locomotive automatically, which is called the flasher lights. They come on automatically, but that system has its own limitations, and therefore. And now we come to the gap which we have been talking about for the last so many days. And the gap is can be plugged only by automatic train protection systems. This gap is basically from the signal to the loco pilot. This is basically a human activity there. If the signal can be mistaken, or if the driver is not active or inert, or the signal aspect has not been properly understood, in that case, there could be cases of higher speed negotiating a speed restriction or signal passing a danger, which can lead to collisions or derailments. And this is the diagram, I think, which is an internationally accepted diagram. You can see that the normal method of working is the top portion of the diagram, which is they're saying that there's a signal and there's a train driver. But you can look at the strengthening loop in the dotted area. The dotted area is precisely the automatic train protection system, which enforces speed commands, movement authority given by the interlocking. The interlocking has to be certified for higher level of safety criticality. And this movement authority can be given directly in the cab, so that the driver responds to it. And in case he doesn't respond to the display, the driver machine interface indications in the manner it is required within 5 seconds or 4 seconds, the automatic braking will take place, and the train will come to a stop, and then that will be registered. It has to be explained by the driver or the loco pilot or the motorman. So this dotted area is the subject area of all of us. This document must be understood by all the signal engineers. so that you are able to devise methods of working on. And now this is the area in which different technologies or different methods of working, different styles of different concepts have emerged all over the world, right from US to Europe to Russia to China to right up to Japan. Everybody has done in a different manner. I will touch upon them briefly. Now, this is what is the slide which I've been able to extract after a lot of research work. We had the first trial in India in 1924. 1924-25, before that was the British Railway. And this trial was done on the then Great Indian Peninsula Railway, which is later on called the Central Railway, and now it is called the West Central Railway. This was done by called the Rose Patent Train Stop Apparatus. This had some kind of a device on the ground and the circuit on board. And this device on the ground was connected to the supply, which was controlled by the signal. If the signal is red, it will convey a battery. If it is not red, it will withdraw the battery. So that was the moment the train locomotive used to pass over this device. And there is a plunger there. You can see the plunger on the diagram on the right hand side. That plunge and that engine tube presses the plunger, and there is a break in the solenoid circuit of the vacuum pipe. And if there's no supply available to hold it, then definitely brakes will be applied. And therefore, that supply has to be a positive act to be extended to the system in case it is green. Green is a positive act, supply is a positive act, and therefore, whenever the positive act is there, that is green is there, then the supply has to be maintained to maintain the solenoid so that the train does not break. In case the power supply is not extended, the brakes will be applied, and that the trains will be brought to a stop. This was a very, very basic system of automatic train protection for preventing SPAD or preventing the impact of SPAD. But people forgot about this because this particular device on the ground was getting stolen. The socio-economic conditions were not very comfortable at that stage, so they were being damaged, stolen, and there were steam engines available. There were problems of different kind of maintenance of this device. And therefore, this had to be done away with. The trial did not continue thereafter. And luckily, it was, at that time, the traffic was so less, maybe 10 to 12 trains each way in a day. So with that kind of a train density, I think the people thought, the officials at that stage thought that it is not worth investing its kind of a work. And this is very evident that even after independence, the first Shahnawaz Railway Accident Inquiry Committee also focused on only the basic signaling and interlocking, which I have talked about earlier, because they were considered enough to prevent accidents. And then later on, we had a number of committees coming in. The 1962 committee, this talked about provision of automatic train control equipment. The Vanchu committee in 1968 again talked about automatic train control. The 1978 Sikri committee also talked about automatic warning and stop systems. And at that stage, I think some activity started. And Khanna committee again in 1998, after the gas accident, talked about train protection warning system and the anti-collision device. And then the recent Kakotkar committee 2012, I've interacted with the Kakotkar committee, and they, after going through the developments in the country and in the world, they also visited the world railways, and they believed that the only system which can be used on the main line, golden quadrilateral and diagonals, for which can give you line capacity as well as safety, is the ETCS level 2, which should be deployed on the main line and the golden quadrilateral and the diagonals. But on the entire branch line, which is 55,000 kilometers, branch line was supposed to be having Indian Railway Train Control System. That was the policy at the time of 2012. Now, how different systems evolved, you can this is a single page slide, which tells you that the very first, in fact, after 50 years of the first trial, the second trial started with the advanced auxiliary warning system on Eastern Railway, that is Howrah, Burdwan and Gaya Mughalsai section, where track magnets were used, and they were damaged and stolen, so therefore it could not be continued. This was in the year 1975 also. The similar system, which was called auxiliary warning system, which Mr. Yadav talked about on Mumbai Central and Western Railways, these systems were later on progressively installed on central and western suburban sections, and they are still working because in the suburban area and the socio-economic condition of that region, I think led to their stable working. There were no cases of damage or theft, and therefore the system is still continuing. And thereafter came the anti-collision device. In fact, after the gasoil accident, there was a concept trial. We'll talk about it later on, and that was the major trial was done in the year 2007 on the Northeast Frontier Railway. Almost at the same time, there were trials parallelly going on ETCS level 1, which we in Indian context call train protection warning system. Indian train protection warning system is different from the British train protection warning system. I think all of us must know about it, that the train protection warning system name is given to a British system also, which is a single company system, which has been deployed, which I'll briefly explain that also later. But these two systems, level 1 and the Delhi-Agra section on the locomotives, and level 1 on Chennai-Gumidi-Pindi section of Southern Railway, and later on we did the same system on Kolkata Metro for preventing cases of SPAD and collisions, especially in the tunnels. And this was done, and although this is not the right solution for metro, but this was attempted at that stage. And in the year 2013, using this the ETCS level 1 concept, they have done it. But now I think they have planned to change it to either communication-based train control, which is suitable for metro systems, or the distance to go system, which is also suitable. Thereafter, after this, when we found that the ETCS level 1 system is extremely expensive, and indigenization efforts were not taking off even for them, parallelly the concept of train collision avoidance system was initiated, of which I think one of the experts is with us, Mr. Lalit Mansukhani. And this concept emerged at that stage only to replace ACD's limitation. ACD's limitation was only one, that that system was from a single source. Single company cannot cover the entire Indian Railways. And therefore, a decision was taken to have a different name, that is train collision avoidance system, because of IPR issues and all. And I think till about 2011 or 12, the intention was to develop multiple vendors for the train collision avoidance system. And that I think Mr. Mansukhani will explain to you that what happened then and how it was later on changed to the Indian Railway Train Control System, which is a much larger concept than the TCAS system. Now, the intention was to either put a modern train control system or TCAS on Indian Railways. That was a strategy. As I mentioned, we have to work for it for the next 10-15 years. And meanwhile, on the metro side, we went in for distance to go system in the year 2002, when the first Delhi Metro was commissioned. And later on, we had communication-based train control systems, because here the control has to be more precise, more correct, more accurate, because the stopping point is defined. You cannot stop anywhere and wherever you feel like the mainline train. But here you have to stop within some, they say it is almost like 35 to 40 centimeters. And that is a very, very precise way of stopping. This I've already covered. I think I'll have to go to the next one. This I've covered. I'll just again talk about it. This advanced auxiliary warning system, which was done on the Eastern Railway, had a problem of theft and damage, and that's why it was withdrawn. And the very same system was deployed on the Western and Central Railway. Now, let us come to the specifics of auxiliary warning system on EMU on Central and Western Railway. This is basically an additional layer of signaling or train control over the system which is already available. This assists the driver in the busy automatic suburban section to prevent cases of free passing in danger and enforces speed restrictions. And if in case there's the intention to pass the signal danger, then there's a emergency braking. The system is based on track magnets, which are deployed depending on the requirements of signals. And at each foot of each signal, there's a device. The moment, in fact, this device is being driven by the aspect of the signals ahead. The signal which is controlling the device, the track magnet, will convey to it whether it is red, yellow, double yellow, or green. And that based on the aspect of the signal which is received by the onboard device for that's called onboard track magnet. When it senses it, then it accordingly, or the onboard microcontroller accordingly controls the speed to the required level. If the speed is not controlled, within 4 seconds, the system takes over and stops the train. This is the diagram. Now, what I mentioned was how the signal is taken from the aspect of the signal. Now, if the red is burning, then you have got an output of 12 volts, which is feeding the signal lamp. That 12 volt output is sensed through optocoupler sensor, where if you physically don't measure the current, but you measure the output voltage, which is driving the bulb. And that voltage is sensed, and based on the sensing of the voltage, it is decoded. I'll say it is decoded, and from there you extract a signal which lights a LED lamp. That LED lamp is linked to the optocoupler, and from there the track magnet. There are different frequencies, frequency combination which are which are configured there. And the moment the track magnet passes over the engine magnet passes over the track magnet, the engine magnet gets the concerned frequency which has been configured by the dynamic situation at that time, whether it is red or yellow or double yellow or green. And that based on the aspect which has been received by the engine magnet, the onboard controller processing unit then takes over, and that gives an indication to the driver what action has to be taken. As I mentioned earlier, that in the case of green, nothing will happen. In the case of double yellow, nothing will happen. Only thing, he has to get a beep and he has to acknowledge it just to see the driver alertness. But in the case of yellow, he has to control the speed to about 38 kilometers per hour, 38 kmph, just almost 290 to 300 meters before the signal head, so that he's able to, the driver is able to stop the train short of the red signal. And if he's above 38 kilometers per hour, this has been arrived at from the braking distance of the EMU. The 38 kmph figure has been arrived from there. That if at 38 kmph, an EMU can stop within the overlap. Overlap is 120 meters. So 120 meters is the braking distance of an EMU at 38 kmph. That is why 38 kmph. And then in case he doesn't go to 38 kmph, automatic emergency braking is there and the train is brought to stop. Second thing is, in case you pass the red at in case you pass the red signal at danger, then again the same thing happens. There's again full application of emergency brake, and the driver has to get on and reset the devices to start again. Now all this is done by a combination of frequencies which are 7 in number, F1 to F7. And you can know that from the mathematics of permutation and combination, you can have 21 different combinations of these frequencies. And they are used for different kind of situations, right from green, double yellow, yellow, red, then calling on, automatic, then route indicator, and then buffer stop. Many different operating requirements are there. Based on that, they are done accordingly. This I think generally covered. I think it can be covered more in detail. There's the onboard cab equipment, the engine magnet, the tacho generator. Tacho generator is basically used for the purpose of sensing the speed of the train and the distance it has moved. And that is used as an input by the onboard central processing unit, and which senses the speed. And then in case the speed is above the defined value or as per the frequency combination received, then the beep will be given, the indication will be given, audio visual indication will be given. And if the driver does not respond, then the train will be brought to stop. At times you find that the onboard equipment or the track magnet also fails. There's an isolating switch available to tackle those situations, that in case something goes wrong, then you must isolate the switch, and then it is in the staff responsible mode. That means the entire train is the responsibility of the motorman. These are some these are some pictures of the central processing equipment, the driving cab indication board. You can see that this is the engine track magnet, and this is the track magnet mounted on the ground. If just at the foot of the signal, you can see the lower picture, and also shown is the optocoupler box, which is actually mounted on the signal, so as to minimize any cable losses and all. And the track magnet is just kept almost over 1 or 2 meters just before the signal, just to take care of the overhang of the EMU also. Now, what happened to this AWS was that in the year 2003, the OEM of this AWS system mentioned that we will not be able to support the system. And then RDSO got into full-fledged R&D activity, and they developed multiple resources in the country. And now the entire AWS is being supported by companies from India. the very same AWS is now working with using the track magnets made in India and onboard ancillaries and equipment made in India. This is the only activity which was very effectively steered by RDSO. And as the OEM was withdrawing support, we had to do something, because the actual system which should be there in the Bombay suburban section should be either distance to go or the communication-based train control system, which I think that is now part of an approved project which is being done by MRVC, that is Mumbai Rail Vikas Corporation. And they have been assigned a project of communication-based train control to improve the headway on Mumbai suburban section. I understand the work has been, some kind of initial work has been started for the Central Railway Harbour Line. That is what the information available with me as on date. Then came the issue of anti-collision. In fact, after the worst accident of the entire century, I'll say 1999 August, the KSL accident, where we had a very bad accident in which two mail express trains ran into each other at the maximum speed, and we had quite a lot of casualties, and everyone in the country was stunned, and therefore and that accident was on account of multiple levels of failures at multiple locations. And the Konkan Railway came up with an idea of a system which is not linked to signals. They say it is not a signaling system, it is not linked to signals, it is a non-signaling system, it is a non-vital system, it is a silent worker just working on the locomotive. And that in case there is a hazardous situation emerging within 3 kilometers of the trains approaching each other, then there's an automatic application of brakes. So this is what is the simple configuration diagram of our anti-collision. I'll not talk much about it, because this particular activity has been now largely embedded, I'll say largely embedded into the Indian Railway Train Control System, with some additional and more features in the system, which Mr. Mansukhani will talk about. But just to mention about that, there is an ACD device in almost every area. There's a station ACD, there's a repeater ACD, there's a level crossing ACD, there's a ACD on the unmanned level crossing gate, there's a approach warning at the unmanned level crossing gate, there's an ACD on the loco shed also. Everywhere ACDs are there. And this is multiple processes are interacting with each other. And the moment the entire concept works on the track ID, onboard computer, onboard ACD or the locomotive knows what is my track ID based on many things. But the concept which was evolved by Konkan Railway was the deviation count theory. And that deviation count theory was that if you are running on the main line and now entering into the loop line, how will your track ID change automatically? And that deviation count theory was used for that purpose, because the GPS coordinates, the moment you have got an inflection, if you go into a turnout and turn in again, you'll get an inflection, and then at that stage, the track ID was changed automatically. And therefore, this was having many times problems. And therefore, during the trials, we found that there were a lot of spurious breakings. So the concept is basically, if the two locomotives are approaching each other with the same track ID, then there will be automatic application of brakes. This is what is the thing. And the inter-ACD communication is through 400 megahertz radio, which is the frequency band available with the Indian Railways. And this was not a problem at that stage. And the GPS coordinates were taken from the American satellites. Now, all of us know that GPS has some errors in this thing during atmospheric variations and all. And therefore, the concept of differential GPS also was brought in. The differential GPS is a GPS device on a fixed installation of which the coordinates are known. And that used to be giving the correction factor to the onboard locomotive through the radio, that this is the actual location of your train at that stage. So with that differential GPS and the deviation count theory, we were able to decode the track ID, and we were able to have a system which was workable. I think the much more work was required to be done, which later on led into the development of train collision avoidance system. Now we come to another device, which is called which I also mentioned earlier, was the British Train Protection Warning System. And we we had multiple presentations on this in the board, and we found that this system is not suitable for Indian condition, because the system has got a limitation of first of all, they are open to theft, and we had problems, as I explained earlier, of thefts and damages to these devices which are on the ground. These are copper devices, although they are passive devices, but they convey to you a lot of things, and that those information, if it is not available, then you may miss the signal, and you may lead to a danger. So this deployment was defined for UK, because there was a serious collision there, and then they took a decision in the year 2000 that there has to be something which has to be done. And the main objective was to initiate a brake command whenever a train is about to pass a signal of danger without any movement authority. Or if a dangerous train is available at a terminal station at a buffer point. At these two cases, they wanted the train to be stopped. This is not designed to prevent SPADs, but is only to mitigate or reduce the risk of consequences of SPAD by preventing the train reaching a conflicting point. Now you can see that there are three devices. There is OSS and the TSS. The OSS is basically a overspeed sensor, which is located before that before the signal and before the trigger sensor, the train stop sensor. Now this sensor actually is meant only to check the speed. In fact, there are two devices there. The moment they pass over both the devices, you can work out the timing, and based on that timing, you will know what is the speed of the train. Your tacho generator is there. You're sensing from both the devices on the OSS is there. You know what is the speed, and then you start decrementing the timing. And if you reach the train stop sensor earlier than necessary, if you reach there earlier, if you're late, there's no problem. If you reach earlier, that means you are going at a higher speed. So if you reach the train stop sensor at a high speed, the trigger loop will get actuated, and if the signal is red, you will be braked automatically. And that is how in the pictorial form I would like to explain. This was an extremely low-cost device, and there was a feeling in the railway board that this can be worked in the country. But for two reasons. One was that it had a lot of metal in this, and second one was that we have trains with multiple braking distances, a lot of mixed traffic, right from 2 kilometers braking distance to about 400 meter braking distance. So to have an OSS for a 2 kilometer train, you can imagine how many OSS has to be provided and how to maintain them. Therefore, this was given up, and this particular thing was, this is a typical diagram of that. It is defined that arming transmitter and the overspeed sensor, which has got almost 6 meters to 36 meters apart. And then there's a trigger sensor. In case the speed is sensed more, and then you can come to them. This is a typical layout. Actual diagrams are based on, in fact, let me also explain to you that many of the Indian signal engineers have gone to UK and done this work between 2000 and 2008. Many. And they are much aware of the system. But when this presentation was done, only one company, which is in the world. So three problems. One is the single source. Second one is the local conditions problem of damage and theft. And third one was the multiple braking distances in this country. So therefore, this was given a go by. We did not go for it. Then we also had a feel of the incremental train control system, which is totally GPS based. And this is the American system, which nowadays they call as positive train control, PTC. And this was initiated in the year 1994, deployed in one of the trains between Detroit, that is Calamar, and Michigan City. And I was on the footplate of this train in the year 1996, not 1996, 2006, sorry. And when there's only one driver in Amtrak. There's only one driver. So when the driver, I was watching the driver reaction, the driver initially was moving in the non-ITCS territory. And when he entered the ITCS territory, he was so relieved that he just left the controls, because he knew very clearly that the system will tell him. The system will tell him when to control, when to stop, and when to, and this system has been deployed. The system is very, very, very simple system. This again based on GPS satellites and radio communication, something more similar to ACD, but this has linkages to signaling. This has linkages to signaling This has to have onboard computer ensuring movement authorities based on inputs it gets from the different sources, right from the conditions ahead, the condition of the station layout ahead, and the condition of the signal ahead, and also the intactness of the train integrity. Train integrity is a very important aspect of ITCS, incremental train control, because if the train integrity is not maintained, then again the train will be stopped. And this concept has also been used in the communication-based train control, where also train integrity is very important. The same concept is also used in ETCS level 3, where also the train integrity is very important. And each of these three systems have used this concept of somehow ensuring the intactness or integrity of the train. And that is very important, because that is the last vehicle of the train is the obstruction point. And this system allows, the only beauty here is, which is similar to the Indian Railway train control system, is that they have got servers at each station. And therefore the communication requirements are minimized. And that network, the way they call it the wayside network, ensures that the information is received by the locomotive from the nearest base station, and the trains are controlled. Here, all the signals are again given virtually in the locomotive, and based on the conditions ahead, the trains are stopped and controlled. Now, when we were on this train, I will give an example, the kind of confidence the system has got. When I was coming on the train, I saw another train entering into the loop line, and there is a in the American context, the loop lines are almost 2 kilometers long, or even more at some station. I could see that the train we were running at 130 kilometers per hour when on approaching to the station, and the other train from the other direction was entering into the loop, and both are moving. Both are moving, and we found that the moment the opposing train enters the loop line and clears the fouling mark, the movement authority on the onboard of the incoming train on which we were there has got automatically updated to the level of 110 or 130 kmph. So this is the level of automation which has been done using ITCS, and that is tremendous. But again, single source and proprietary protocol, and therefore not much could be done. But this particular concept and system should be used on sections where captive locomotives are there. Captive locomotives are there, like the KK line. On the KK line, the entire fleet is captive. So you must create line capacity there using this system, along with the higher level of safety in train operation. More details about this system can be, if somebody wants, they can approach me, I will give it to them, because I have made out a complete report on that during my visit to this system. These are the devices which are available. And this is the driver's photograph with whom I had traveled. And on the right hand side, you can see the end of train telemetry device, the orange color device is the end of train telemetry device, which again is important because of the integrity, train intactness of the train. This is all systems are also linked to the CTC. The CTC controller knows where the train is and how it has to be steered. The middle picture, top middle picture is about the radio and the remote area, which keeps transmitting this. Now let me tell you this particular concept was not had not gone anywhere in the world except China, and that was the Tibet line, which was commissioned way back in 2006. This is a concept because the Tibet line, the condition in the field are very, very harsh. It is not easy to maintain equipment. So this is a system which has got minimum ground equipment. It has no signals at all. It has no signals at all, even at the home signal also. And with the control of the onboard control and the centralized traffic control, they were able to pass on the movement authority to the train. And this has been later on recently, about 2 weeks back, it has been further extended in China itself. The only other application of this same concept has been in Australia on one of the lines, which is the freight line. But now I think with the positive train control spread all over US, this concept has been deployed, and they have been now able to develop, I think, 2 or 3 more vendors. So this is what in brief about the incremental train control system. Similar action was also done by the Japanese railway system also, which I been able to get only one slide. And they have been using the same concept. The concept is all the same. You locate the position, locate the last vehicle of the obstruction, transmit the information to the locomotive on cab processor processes the data, and then you have the movement authority defined accordingly, and the braking curve defined accordingly. So this they call it attacks, advanced train administration and communication system, which is used in. They are using again the 400 megahertz band for radio communication. Now we come to the issue in which we have done some work in this country, and this was the onboard train protection systems on main lines in India, which is called the European Train Control System, ETCS. I hope I'm audible.
Yes, sir. Yes, sir.
Okay. So now this is a work. This was attempted because we believe that almost 10 to 12 years of proven experience was there. This was the initiation done in the year 2000. Actually, the original project was sanctioned in 1997, but till 2003, no, not much of an action could be taken because the system was still evolving in different stages in the European system also. And in the year 2005, when we were doing ACD, we also went ahead with this. In fact, this was the only tender in the country which was done without any estimate. This was the only tender both for Southern Railway and Northern Railway, that is the Delhi-Agra section and the Chennai Gumiti section of Southern Railway. This was the only tender which was done without estimate because we had no idea about the costing. And this system has features which all of us know now by now: prevention of SPAD, onboard display of distance to go, continuous train speed supervision, and optimization of train running using infill policy. The infill policy is a very important concept in the case of ETCS level 1. And this is a incremental updating of the, not a continuous, is incremental updating of the movement authority. And this also, the system also can enforce permanent and temporary speed restrictions at work sites and in special bridges or structures or points and crossings. This is what we have done in the pilot projects and of train protection warning system. The Balise transmit the telegram from the LEU to the BTM. BTM is the Balise transmission module, which is on the locomotive. And then this particular air gap, this air gap between the Balise, which is on the ground, and the onboard BTM is standard. The BTM transmits a 27.5 megahertz downlink signal, and there's an uplink which is 4.234 megahertz signal, which is a moderate signal depending on the condition of the signal ahead. That is configured. If people are interested, we can give more details about it because this is a document runs into about something like 20,000 pages. If you look at the subset 26 of ETCS, that is almost like 80 pages of only talking about specifications of how ETCS level works. But definitely the broader concepts can be explained. So the Balise is now available, and this Balise is linked to your LEU, through the LEU to the signal. Now that LEU can be interfaced either at the interlocking with the interlocking or with the signal directly. Both are possible. Both that things have been done in this country, and we have been able to. The beauty of this system is, the beauty of ETCS is that it is the only system which is open specification. Anybody in the world can use this specification to develop the system. Any country. China has done it, Korea has done it, South Africa has done it, India has done it. So any country in the world can use this. That's for open specification. This is called multiple vendors. That is the second very important aspect. Multiple vendors. There's a UNISIG group of companies, which are almost 6 to 7 companies are there, which are totally interoperable. And this interoperability has to be certified by notified bodies. They are called NOBOs. Notified bodies certify that yes, the Siemens equipment can work with Ansaldo. Ansaldo can work with Thales. Onboard can be of one company. Ground equipment can be of other company. All these things are happening in the world. And therefore, in the third important aspect is the interoperability. That means that they call it TSI, technical specifications for interoperability. These three concepts of ETCS are very important. That precisely was the reason for the Indian Railways to adopt the system of in the first pilot project between Delhi and Agra and the later projects. These are the typical diagrams of Southern Railway TPWS. And so this Southern Railway activity was for a distance of 48 kilometers, about 149 signals, 108 LEUs were installed, and about 77 plus spare EMUs. I think 80 plus, total 80 plus EMUs were there. They were all equipped and they had to be fine-tuned. I would like to acknowledge the effort made by Mr. Kashinath, I think the first member signal. And he was the person who was instrumental as CST construction of this railway to fine-tune it in the year 2008. And this was commissioned. And at the same time, parallelly, you can see the photograph of the on DMI. This DMI also is not the European DMI. This is the simplified DMI for Indian requirements. And that is how it was configured. I remember the first time I went in 2006 to the site from the railway board, we did not know where to mount them. So we made out a wooden replica of each of the equipment. We made a wooden replica of the tacho generator, wooden replica of the DMI, wooden replica of the brake interface, wooden replica of the BTN, and the onboard computer. And then we tried to find space on the EMU where to fit it. Similar thing was done in the Kolkata Metro also, where we had to, the old stock was available, old coaching stock was available. We had to find space to keep it. And this is one of the bigger exercise for all young installation engineers. They must understand that the way the equipment is manufactured, that cannot go straight away and fit into your system. You have to reorganize your cab. You have to reorganize the loco area so that you are able to, and you have to also reorganize the cabling area. And the cabling also is of a special kind, which has to be fire retardant or fire resistant. So all this was done, and then we could commission this in Southern Railway. This is another block diagram of TPWS. Now this is a typical legends. All of us who are in the field of signaling know there's a thing called signaling plan. Now we had to devise a plan to depict the location of the balise, because the location of balise is very important. The location of balise from the signal which is controlling is very important. The location from balise to balise is very important. And therefore the concept of balise plan emerged. And that is basically an additional layer of information on all the signals which we already have of balise plan. And that is what I'll show in the next diagram. This is a typical balise plan. This is a typical signaling plan, but we have also shown some, you can see some red arrows on the track and black arrows. These are the arrows which are basically balise locations. And these balise locations, you have to also define the distance between the two balises, because each balise, which is getting the information of the balise ahead also, along with the distance at which you will locate the balise. And that purpose is only for the purpose of distance or location correction. That purpose is for that purpose, along with other information about the track, the gradient, the curve, the points and crossings, and the signal aspect ahead. Now this is the one which is can show that when you enter a balise TPWS area, you have to have a big metal mass balise. There's a separate kind of balise which tells you, which tells the onboard that you are entering into the ETCS level 1 territory or ETCS level 2 territory. So you get the word uses big metal. You can see at the left hand corner or the right hand bottom corner, big metal mass balise. This allows the onboard to sense it and it decides. Yes.
Sir, the presentation is not visible. Kindly reshare it, sir. I think.
Okay.
Sir, it's visible now.
Okay. So what I was talking about, that this you must know, the onboard must come to know when are you entering the ETCS territory or the TPWS territory. So that is being ensured by a big metal mass balise, which is sensed by the onboard, and they are two balises in one after the other, and they are sensed, and then accordingly they convey to the onboard that you are now entering the onboard. The onboard, the booting system starts, the onboard computer starts, and then is ready for the next information. The next information is about the balise which is available next. And that balise gives information about each signal. You can see there's the green balise in between. This green balise is, as I mentioned earlier, is very important. It's called the infill balise. Black balise is a normal balise, but the green balise is called the infill balise. This infill balise is basically for the purpose of ensuring that you don't lose time or lose running time or lose speed. Just visualize that, have a situation that we have got a level crossing gate and the signal, let us say S124 is red. And by the time the train approaches, you find that the level crossing gate has been closed and the S124 has now become green. Now, if the train has already passed signal number 116, that means the balise number 2707 it has passed, then it is about to brake now and come to a stop. But the moment it passes the balise number 2709, this which is called the infill balise, it gets a command that the signal 124 has now gone to green. And therefore, immediately the movement authority is updated and the distance to go also is updated. And he need not brake, he can then increase the speed. So this is the very important feature, especially in the Indian context, because if you start stopping like this, we will be only eating into the line capacity. And let me tell you, signal engineers' primary focus may be safety, but my focus is basically the safety at the maximum permissible speed, with maximum number of trains following each other at a very close headway. Our intention of safety is not to stop trains and then be happy about it. The signaling means maximum speed, minimum headway, and maximum safety. And that is what this infill balise allows you to. There are systems available which give you continuous update, which are either radio based or there's called Euroloop based, which have not been tried in this country so far. This is a typical diagram of the Northern Railway project where we did balise again. And you can see the balises here. The first balise is always two balises, one after the other. And then you can see that the blue dots I just tried to show you. That the complex yard also have been covered. But we have taken care that in major complex yard, only the main line, the first loop has been covered in the first. Because after the first loop, the speeds are very low. And there's no point in investing such a large amount of money on the second and third, fourth loops. So for my main line in the first loop, we have been able to configure with the required balise. This is that earlier one was the station diagram, and this is the section diagram. And you can see the balise and also the infill balise. The infill balise connection is there. And this linking is very important because this linking is in two manners. One is it updates the aspect, the dynamic condition of the signal. And second is it conveys the distance at which you will get the next balise. And that distance is very important because that is actually measured and configured in the system. And that distance corrects in case there is a problem of slip and slide, which takes place in the case of rolling stock. On down gradient or up gradient, you will have a slip in the case of down gradient and slide in the case of up gradient. So these slip and slide will lead to the tacho generator behaving erratically. And therefore, there has to be a system correction. In the case of Kolkata Metro, we have used radar for this purpose, for slip and slide correction, because the requirement of stoppages at the platform is very critical there. These are some of the devices which are onboard devices. As I mentioned earlier, that a lot of initial work has to be done to see where to mount and how to mount various equipment which are part of the ETCS level 1, which we call TPWS in this country. And this all requires approval from the concerned department and the concerned directorate of the RDSO. In fact, the mounting of balise also requires approval of the Civil Engineering Track Directorate, because without their permission, you cannot. They are mounted on the sleepers. These are some of the pictures of Kolkata Metro TPWS, which gives you the trackside balise as well as the LU and the onboard equipment. This, I think, there's only an informative slide. We have discussed about all these aspects in this. Now we come to the issue of level 2. Now, why level 2? Level 2, actually, the intention was that we need to have trains at closer headway. The current headway between trains in the Indian context on very dense sections is of the order of 12 to 14 minutes, 12 to 14 even more. And if it is a freight train, then it is even larger, almost 25 to 30 minutes. So this has to be reduced to the headway requirement of 6 minutes. Now, how to do this? And therefore, that's the strategy right from 2003 was that ETCS level 2 will be deployed on all the golden quadrilateral and diagonals where the line capacity is totally saturated, and we need line capacity there, along with the basic requirement of safety in train operation. That means enforcing speed prevention, preventing collisions, and preventing derailments on account of high speed. And this diagram is known to most of the signal engineers. That is a system of one. In fact, in the case of ETCS level 2, this also is an overlay system. And the only thing is that you can avoid the signal in the section. Without that signal, you are able to give the line capacity. In the case of automatic signal, conventional automatic signal, you have got signals every 1 kilometer or so. But in the case of ETCS level 2, you can provide line capacity without providing the track side signals. Now, the only the basic requirement is the train location determination. Train location determination continues. It continues to be with track circuits or axle counters. And this has to be continued because the train location has to be known. And therefore, a lot of studies were done. What should be the length of the track circuit? What should be the length of the track circuit so that you are able to optimize on the line capacity? Because if the track circuit is kept 2 kilometers long, you will occupy the track circuit for a longer period. and sorry. I'm sorry. So you will occupy the track circuit for a longer period, and you will spoil the line capacity because the train which has been following you cannot be given the signal. Therefore, there was a study done, and we'll come to that also later on. But here I'll just talk about the principle. The principle is very simple, that the onboard location is transferred to the radio block center, and the radio block center then conveys back to the onboard that this is your movement authority. You can come to so-and-so point. You can see the axle counter, you can see the point machine, you can see the marker board. Marker board are basically in lieu of signals because you have to still tell the driver to where to stop. In case of an obstruction ahead, he has to be given a marker board where to stop. So these marker boards are for that purpose. Otherwise, Eurobullies are there for the purpose of, in fact, Eurobullies is for the purpose of even location correction also in this case. So this is in brief the entire concept. The radio block center decides the movement authority to be conveyed to the onboard, which is through the optical fiber to the radio, the nearest radio, and the GSMR. And the project which was conceived for the Indian context was that since GSMR is becoming obsolete and is not going to be supported beyond beyond 2030, and therefore there was a strategy to work on other systems which are either defined by 3GPP release 14 or 15 specifications by the 3GPP group. And then they are basically in the 4G concept basically. But parallelly, the work also was taken up for the FRMCS, which is called the Future Rail Mobile Communication System for all the applications on board, include security and train ticketing also. So now coming back to the GSMR did this job wonderfully well for ETCS level 2. And we found that it was deployed in China on a very large scale. It was deployed all over Europe in a very large scale, and in many other South African countries and even South East Asian countries, Middle East countries. So this particular project of modernization of train control system in India, we conceived that we should go in for evolving our concept for the Indian conditions using the ETCS standard configuration along with LTE as per the 3GPP release 14, 15, 16. But currently the state of the project is that it has been kept on hold because of some reasons. In fact, we even asked for a bandwidth from the 700 megahertz range, which I think will come useful for IRTCS also, that is TCAS. And that just about a month back, it has been awarded. This frequency has been given by the Government of India free of cost to the Indian Railways, but the bandwidth is only 5 megahertz. And that is with the condition that it will be only used for security and safety purposes, not for commercial activities. And therefore, that project is now being reconfigured, and let us see how it happens. Now, in the Indian context, so far the line capacity, what we were doing in the Indian context was basically it is the track section which decides the line capacity. If the track section is properly worked out, and this is definitely a very, very big design problem in the Indian context. You can see that in the Bombay suburban section, the track sections are hardly 350 to 400 meters. But at the moment you go beyond Virar, it comes to 1 kilometer. And in some sections, 800 to 900 meters. And this is all for the purpose of catering for the needs of the worst case braking distance of a freight train. Because we have got on the same track, a mail express train running, a memo running, a high-speed train, everything running on the same track, a stopping train running on the same track. And they have got different braking characteristics. Therefore, there's a need for this kind of a situation that we need to work on a concept which can take care of this. So ETC level 2 took care of this to a larger extent, and then the onboard knows about the movement authority from the RBC, that is Radial Block Center. So there's a problem only in the case when there's a slow train ahead of the fast train, and that really puts the pressure on the literally push the pressure on the line capacity. It totally spoils the line capacity. And these are some of the standard, I think, documents which I think many of us know. This particular optimized track section was for 400-meter block everywhere. This 400-meter block everywhere was a concept when you can get a line capacity increase of 37% as compared to the base level of level 1. If you've got level 1 already, then above level 1, you'll get a capacity of 37.7% extra. And this capacity was the driving parameter for the modernization of train control system project in the country. This is another description of the same chart. And the level 3, I think all of us know that there are no track circuits also. And therefore, as I mentioned earlier, that the system of ITCS, incremental train control system, uses end of train telemetry. This also has to use some kind of a train integrity mechanism, which is shown in the yellow box. This is very important. Without this, and the balise is only for the purpose of location correction because of slip and slide. So this level 3 is still far off this thing, but I think NCRTC is using this concept along with level 2. They call it a level 2 hybrid or level 3 hybrid, in which they are able to divide the track section into virtual sections. And we have to only see that project coming up. I think the bidding has been done, the contractors have been fixed. Let us see how it develops. This will be again an indigenous concept where we will be doing hybrid level 3. That means basically the system is level 2. But if, within the level 2, you also have level 3. The track sections are still there. But within the track sections, if you feel that you want to come closer, then there are virtual track sections created by the system. And those are the concepts of level 3. Because the integrity of the train in the case of metro systems or NCRTC is very, very clearly defined, because the moment there is a parting of the train, the locomotive, the train set will come to a stop. And therefore, the concept is being attempted here as a ETCS hybrid level 3. These are some of the information which I think everybody can take a look at that. This is, you can just, we had to collect this information while drafting the project. These are some of the specifications which are mandatory. The most important subset is to the subset 26, which defines the system requirement specification for ETCS, level 2 and level 3 both, and level 1 also. And then we have got the specific mandatory specifications for driver DMI, for Euro balise, for Euro radio, for RBC handover, and for and the engineering rules to be how to configure them, how to define them, and the communication interface between RBC to RBC and GSMR to RBC. These are some of the other specifications which are not that stringent, but they have to be still followed. The RAM requirement, odometer, then testing requirements, safety analysis. These are basically documentation work to give you confidence. Yes, my system is safe enough, my system is working, my system can work. This is typical architecture which we have taken from all the subsets we have defined in this. In fact, this architecture we have made in Railtel, and this architecture now defines, instead of the GSMR, we will be replacing it by the by the LTE. This is our diagram which we made in a slightly simplified manner. But this project, as I mentioned, is on hold, and let us see how it comes. This is not necessary. Now I come to the last part of my presentation, where I will request my very good friend and colleague, Mr. Lalit Mansukani, who is also my college junior, who was my colleague in Department of Space, Indian Space Research Organization. We were together there for some time before coming into the railways, and we have done a lot of work in this area. But I have only one interaction with him from the board when he was conceiving the system in the year 2010. He was working on the specification, and he had big plans. He had big plans. He said that he will not talk it as an anti-collision device, but he will talk about it as an Indian railway train control system, or the indigenous train control system, which will take care of all the requirements of Indian railways. All means all, including line capacity, that means the headway requirements, including safety anyways paramount, high capacity requirements, including requirements for running at high speed, and the requirements of, in fact, one of the very good features, I think, which he will explain also, is that because our drivers are used to seeing signals, so our DMI of TCAS also shows the signal, which I think I will be having it. Yes, this photograph shows here. This photograph shows there's a signal also, which is not there in any of the DMIs anywhere in the world, except I think in the case of ITCS, where they show some light there, but the signal is shown here. Second one feature of which is very important is that in case for some reason the train is coming on a wrong line, and that scenario also, I'm told that TCAS is able to stop the trains. I think Mr. Mansukani can support that argument. These are some of the pictures which I have been able to get. As I mentioned, that the entire concept was evolved in the year 2009, 10, 11, and the specifications were made. But in the year 2012, they really froze the specification and called an expression of interest for doing the first trial of 250 kilometers on South Central Railway. And the South Central Railway trial was a wonderful trial, and it went off well. I was also on the train along with the Chairman Railway Board, and Chairman Railway Board was thrilled to see that. In fact, we created a collision. We kept a locomotive in front of us, stopped, and we came at full speed. And we found that we were able to stop short of the obstruction, that is the locomotive. And everybody was scared in case on that day if the system didn't work. But the system works, and system definitely works, because the concept used is based on the defined principles of Senelec 50126, 128, and 159. 129 and 159. So I think I will now leave the floor. I think this is a separate subject. We can talk about this. Communication-based train control is primarily for the metro systems. We can talk about this subject later on. This I will not like to discuss because there will be a controversy in this. So there's a lot of comparison done between TCAS and level 2. So I think I'll have to skip this and this. Thank you, all of you, for the patient hearing. There will be a lot of questions, I know. And I will now request Mr. Mansukani, who is a very, very competent and established colleague of mine, very dynamic and very focused on this subject of, in fact, even working as an additional ADRM, he was focused on this project. And I understand that he's trying to move into this project slowly. So we will definitely say the technical aid to the driver is a must, and all the queries you can send it to me directly. You can take a note of my email ID, and other things can be done by.
Thank you so much, sir. Thank you so much for this wonderful presentation. And I welcome our third expert, Mr. Lalit Mansukani, to share his presentation. Thank you.
Good evening, Sumit. Am I audible?
Yes, sir. Yes, sir. I'm sharing the video right now.
And you can pause at 27 seconds. Sir, actually, since time left is too less, so I will start with one particular video which shows resemblance between ETCS level 2 and TCAS. And before starting the presentation, I should say thanks to Arun Saxena sir and Rail Academy to give me opportunity to present this. Sumit, can you display the video, please?
Sir, okay, so video is not being displayed. Okay, just a moment, sir.
Actually, this is one animation video, and through this animation video, we'll try to understand like what is the difference between intermittent update and continuous update, because there were some certain mention and queries in the chat box. So I thought, since time is short, let me first cover this aspect. It will be good.
Sir, is this?
Yes. Now you come to 27 second. Skip this portion and come to 7 second. Yeah. Please pause here. If it can be made full screen, then viewers will be able to appreciate better. Let me tell you. Actually, if you see this particular animation, we are here comparing ETCS level 1 type of system, which is intermittent update type of system at the top, and the same set of signals or moment authority to the ETCS level 2 and TCAS, which are both continuous update type of system. See, our signal number 4 is presently at red. When the train moves, pause please. Our signal aspects will change when the signal is on. When the train is on approach of signal number 2, then like the first cautionary indication will go to the train and driver that some signal ahead is at danger, and be ready to apply the brake, and braking distance should be available between signal number 2 and signal number 4. Let us Sumit, cross the signal number 2. Please pass the signal number 2 and pause. Little bit more. Let us go ahead and pause here. Pause please. We are able to see that braking curve. Now when the train is on approach of signal number 3, okay, so machine as well as driver both understand that the next signal is at danger. Okay, so brake application should have commenced by this time. If driver has applied the brake, then no issue. Adequate brake, no issue. If brake is not yet applied, then by driver, then the system, train control system, will apply the brake. Top, again I am repeating, top half is ETCS level 1, bottom half is ETCS level 2 and TCAS, because both are getting moment authority through radio communication, as you can see. Whereas in case of ETCS level 1, top half, the moment authority is being transferred to the onboard through Eurobellies, which are installed at the foot of the signal. For simplicity purpose, I have not shown infill bellies because it is very clumsy. So presently, you can see one level crossing gate ahead of signal number 4, between signal number 4 and 5, which is now at present open to road traffic, and the signal is therefore red. It is outside the overlap. Okay, so signal number 4 is red. Now let us, Sumit, let us pass the train beyond signal number 3. Here at signal number 3, onboard has got picked up the information. Now please pause. Now train has already passed the signal number 3. Now next signal which will be encountered is signal number 4, which is supposed to be red. Machine has also understood, and train loco pilot also has understood. Till this time, ETCS level 1, ETCS level 2 and TCAS all have behaved identically. Now I will request just little bit, when signal number 4 becomes off other than red. Then pause. Please pause. Please. It is speed prevention. Now I will tell you. Signal number 4 is red, and but here you can see this signal number 4 is red because of level crossing gate. But suppose level crossing gate is subsequently closed. Okay, then what will happen? Then signal number 4 will no more be at danger. But how the machine will come to know, driver will come to know when he is approaching signal number 4. He or she can see that signal is no more off and can release the brake and advance the train. But machine will come to know only when it touches the corresponding Eurobellies, which is at the foot of the signal number 4. So even if the signal is cleared, machine will come to know only when it goes near, and therefore we are required to, because of this inherent limitation of the ETCS level 1 system, we are required to make the train to touch to the Euroballis, which tells whether the signal is still red or it is no more red. Okay, even if the signal is red, the train is required to come up to the foot of the signal until some other arrangements are done. So here we can see signal is red, and the train is required to come up to signal number 4. It has to touch. Therefore, the brakes are released, and the train is to be moved to signal number 4. Please move the train to signal number 4 foot. And then stop. Yeah, please stop here. Now see, now in ETCS level 2, we know that signal is definitely at red. Had it not been still red, it would have got updated information that it is no more red. So we can stop before the signal. Here, only after encountering this ballis, the train will come to know in ETCS level 1 that signal is red. Now there are two conditions. Signal is still red, which we are showing in this slide. So after crossing this signal, emergency brakes will be applied and train will be made to stop in the overlap. Please cross the signal. Sumit. Yeah, you see emergency brake is applied and the train is stopped within the overlap. So actually, if please pause the animation here. In intermittent update type of system, this is the limitation that the train has to pass the signal unless until some other arrangements are done which have got other disadvantages. So now here I will tell you on Indian Railway what we have installations. Those are ETCS level 1 installations. What Arun Saxena sir and Mahesh Yadav told in Delhi Agra section or Chennai Gumdi Pundi or Kolkata Metro. So here this particular aspect we have to see limitation. We have to see that the train will stop beyond the signal. It will actually make the speed, and then it will step on another thing, that release speed. Release speed has to be very critically defined. For goods or freight trains, it will be too less, and when the freight trains release speed will be too less, either the train will stop before signal or it will stall, or it may cross the overlap also. We had
Sir, we are not getting your voice. Okay. Fine, sir. Fine. Right. So please join. Please join. Yes, sir.
Thank you, Sumit, for helping quickly, promptly. Now let us go video ahead. And next case we will consider, in which signal number 4. In this particular case, we have seen that signal number 4 remained at red. In next animation portion, we will quickly see that signal number 4 level crossing gate is closed and signal number 4 clears when the train is on approach. Please go ahead, Sumit. Yeah, animation to be forwarded. Now let us come closer to signal number 4 and then pass the signal number 3 and pause. Now pause, please. Now in this case, let us see if we go little ahead and see the change in signal aspect and then pause. Sumit, signal number 4 aspect should change. Please go ahead little bit more close. See, brake is getting applied in both the cases. Yeah, please pause. Yeah, here signal number 4 is no more at red. This information could be conveyed then and there to bottom portion, that is TCAS and ETCS level 2, because it is continuous update type of system. So train went ahead, brakes are released and went ahead. In upper half, if you see ETCS level 1, driver could see on approach that the signal has cleared, but machine is not able to learn this particular change. It would learn only when it touches that ballast. Now see, level crossing gate is closed and signal is 4. So now from here onwards, it is the undue braking which will take place until train or onboard learns that signal is no more red. Now please move ahead the train up to the ballast, Sudhit. Now on touching the ballast, train comes to know that it is no more red and it went ahead. Brakes were released. So this undue braking, now you see, consider we are planning to, I think rest of the things we can avoid in this video, and we can close the video. Now it is already 9 o'clock. So shall I touch my presentation or what? And before that, let me tell you, on Indian Railways, when we are planning for ETCS or TCAS, so we should have such type of train control system, which is continuous update type of system. We have already seen the disadvantage of intermittent type of system. ETCS level 1, suppose we are installing on our golden quadrilateral, already it is saturated. So most of the trains will find attention aspect, double yellow. So double yellow or yellow. So undue brakings will continue. Since the lines are saturated, traffic is saturated. So continuous update type of system only is suitable system for Indian Railways. And here I will mention, Saxena sir has mentioned in his presentation the recommendations of Kakodkar committee. Kakodkar committee recommended in 2012 that Indian Railways should have, in fact, we also presented there, that Indian Railways should go for ETCS level 2 or equivalent system, not ETCS system. ETCS level 2 only has got continuous update feature. So actually, if you see ETCS level 1 system will reduce the line capacity to a certain extent, whereas ETCS level 2 system, level 1 reduces the line capacity, whereas ETCS level 2 has got capability to enhance the line capacity. But it needs radio communication. Now, since time is very less, I will may I request for 10 minutes. I will simply, instead of showing presentation, I will simply discuss and I will come to the last slide, sir. Can I go beyond? It is already 21 hours, 9 o'clock. Please tell me, Sumit.
Yes, sir. Sir, let me just ask the participants. Participants, if you're people who would like to actually extend this session by 10 minutes, please type in yes in the chat box so that we can know. Or okay, sir. Yes, sir. Please go ahead.
Okay. Then let me, instead of showing the various slides, let me tell you like extempore. Okay. So actually, as Saxena sir told that Indian Railway came up first with indigenous system, that is ACD, anti-collision device, that was product of KRCL, Konkan Railway, and it was installed at a couple of places on Indian Railway. But it was not a signaling based system or train control system. It was like something like, taking information from GPS, trying to know the location of the train, and if two trains are found to be on the same track and approaching each other, then brakes will be applied, and so on and so forth. And Rajesh Patel also is there, and a lot of other people I am sure are there who had worked on ACD. In fact, I was also dealing ACD for some duration in RDSO. So ACD's deviation count theory is there, which tries to find out when that crossover is negotiated. But actually, it's not fail-safe system, number one. Number two, undue braking cases were also too many. You can consider, like, accuracy of GPS may not be quite good. In fact, DGPS also may not be that much good. And of course, for, you can say 99.99% time of time duration, this will be this much accuracy. But suppose you just consider, like, if we are on track number 1, and suppose we want to and suppose system detects that it is actually not on track number 1, it is on track number 2. Then all the information which onboard has got will, get false. So this continued, and on in 2008, actually I was not in RDSO. I joined RDSO towards the end of 2011 only, but since I have studied the history of this, in 2008 Railway Board directed RDSO to develop multiple vendors for ACD, because at that time we had got only one option, ACD. So for interoperable multiple vendors, you need to have interoperability. So for interoperability, what do you need? You need packet structures first of all, then other things also are required. But that was proprietary of KRCL. So KRCL never shared those packet structures. And in RDSO, we know RDSO kept on changing the document from version 0, then version 1, 2, 2.1, 2.2, 2.3, 2.4, like that. But it remained on paper only. The document remained of around 20 pages document. I still see from 2008 to 2011, and no packet structures, nothing could be obtained. And finally, RDSO thought to go for EOI. And EOI under the name of TCAS. From 2008 to 2011, TCAS was synonym of ACD, but TCAS didn't have any detailed information. So they thought, let us go for EOI, and if at all KRCL is no more, KRCL is still not sharing the packet structure and all, then let us develop on it on our own, and it will take around 4 years. That is what in writing Railway Board and RDSO entered ACD type of system development from scratch to take 4 years with multiple vendors. Now here in 2011, I also joined RDSO towards the end of 2011, and we thought instead of pleading KRCL to share the packet structures and all, let us develop some train control type of system, which has got SPED prevention facility also. Let me tell you, ACD doesn't have SPED prevention facility, and there has been one head-on collision accident between one locomotive and passenger train in NF Railway, in which ACD was fitted, but SPED prevention could not be made for the loco, could not be stopped because it doesn't have feature of SPED prevention. So collision took place. But here we standard train control system need to have this thing like SPED prevention, supervision of speed restrictions, etc., etc. So here we thought of going for it, and of course it was too ambitious. And Mahesh Mangal sir was in RDSO, and our learned person Arun Saxena sir was in Railway Board, and we got full support from everyone. Of course, this was too ambitious. And another problem was that, as we have seen just now in our animation, that the continuous update type of system needs radio communication. Okay, because ballast can give only intermittent type of update. So radio communication, what was the problem at that time in 2011-12? Actually, at that time, ETCS level 2 still, of course, was based on GSMR, that is 2G technology, and ETCS level 2 was already running. It was already developed. It was in function also. It was started getting commissioned by that time. But Indian Railway was to develop this system which we proposed from scratch. So it was, meaningless to develop the system based upon 2G technology, because it was going obsolete. It was phasing out, and components were not available. People were not coming forward for installation, and naturally it would have taken a couple of years. When ACD type of system, we had told that 4 years it would take. Naturally, this TCAS or train control system will also take that much time at least, and with it is still 4 system and all. So finally, 2G option was not there, because had we developed with 2G, it would have got obsolete by the time product comes up. So that was out of question. Then 4G had not come at that time. In fact, not only 4G, we have to go for even after the introduction of 4G, we have to make it certain adjustment to suit railway requirements and all. So 4G also was not an option, because 4G was not at all available. So we thought what to do. Then with very humbly submitting, then I came up with one communication scheme immediately on joining RDSO, and That is actually TDM, TDMA, FDM, FDMA based communication scheme with space reuse in with space. So SDMA also you can say. So it was little bit fit for purpose communication scheme. Here we did not require voice communication and all. Let me complete my talk within few minutes because it is already it has gone beyond 9 o'clock. So then what we did actually, then we tested this particular scheme. It is different from 2G and 4G, and we tested first in lab, then we tested in field. Then as sir told that, then in 2012 we made field concept trial, and the spread prevention by first ever spread prevention by any indigenous system, field concept trial, and we made presentation to CRB and so many other committees and all. Railway board members also had come, AIMS committee also had come. Then one by one we went for it, and as sir told that we should we aimed to have interoperable system. Interoperable system means all the packet structures or the specifications are to be open. So in TCAS also we followed the same philosophy what is there in ETCS level 1 or level 2, you can say open structure, open architecture. But if you go for open architecture, then the requirement of secure radio communication becomes very difficult. But of course, we could achieve that also. So with that, I will just tell you that we one by one we kept on. First it was R&D phase, so we took around 1.5 to 2 years to develop the system in limited 32 kilometer of section. Then within 3 months, once our R&D was completed, in 2015 we completed all 250 kilometers area. And then in June 2015 we did one more thing. Initially TCAS, or see, name continued as TCAS only because there was some issue of the project was sanctioned in the name of TCAS, but TCAS before 2011 was synonym of ACD. TCAS after September 2011 was actually train control system having capability of spread prevention, which we have witnessed number of times at field. So in 2015, what I was telling that initially we thought that TCAS will not be, it was out of scope to go for automatic signaling. But in 2015, we took up Lingampalli, Hafizpet, Sanat Nagar, that is auto signaling section. At each station, the system was installed by our three developer firms. The system has been interoperable since beginning. So here we demonstrated video reports, everything is available, that we went for the system which can increase line capacity beyond what is achievable through auto signaling. Actually, auto signaling increases line capacity because headway is shorter. It is a signaling section, auto signal section. But if we further reduce the headway by considering track circuit section alone, maybe auto signaling section is of the order of 1 kilometer, then track circuit section will be of the order of 300 to 400 kilometers. So spacing could be further reduced. So we can further increase the line capacity. And here let me tell you, since day one, the train control type of system, train control type of TCAS, like after post September 2011, it is movement authority based. But when we started developing, as it has been pointed out earlier also today, that we were given 3 tasks. First off, you go ahead with the features of train control system like speed prevention, speed restriction, supervision, etc., etc., and that too with continuous update type of system. But please display signal aspect also. That there was one project OBDSA. We told that we'll display signal aspect also, but signal aspect doesn't have any meaning. It is just for the display purpose. Braking, etc., since day one is assessed on the basis of movement authority, which is transmitted from track side to the train. So we can simply by giving like either we can switch off the signal aspect from configuring one parameter in the onboard, or we can give command from station. In station packet there is one bit which says signal aspect off. So signal aspect is of no meaning other than display. And one more thing was that, like, we were asked to not to leave any of the ACD feature. which were non-signaling features also. So we could successfully, with this communication scheme, which has got direct loco to loco or direct onboard to onboard communication feature also, we could achieve those features also. So and multiple frequencies also, multiple time slots and all, we can do it. Initially we did not have sufficient spectrum. Once the spectrum was allotted, we could use FDMA also, and the FDMA was also tested in 2016, etc. And after secure radio communication, we could get the SINPort certification also. Since time is short, I will we can see this somewhere else. I'll hand over to the Sumit, our host.
Lalit
Thank
sir.
you.
Lalit sir, thank you so much for the insights that you've shared in this short span of time. So there is a lot of requests from the participants that we organize a dedicated session on your presentation along with questions. So even Arun Saxena sir has also suggested this. So what I would request that we can pause the session today right now and plan another session dedicatedly on your presentation for the participants. I hope this will be something we can plan.
Yes. So nice of you. And actually, since time was short, so I just spoke something so that people can get some idea.
It's absolutely.
And
thank you so much. So with this, I would like to conclude today's session, and I would like to thank all our eminent speakers today, Mr. Mahesh Yadav, Mr. Arun Saxena, and Mr. Lalit Mansukani. Thank you so much, everyone, for taking out your precious time and sharing these insights with our participants. And most importantly, I would like to thank all of you for taking out your time for our masterclass. We will continue to endeavor to bring such valuable sessions for you. Thank you so much on behalf of Railway Academy. Thank you.
Just to conclude.
Yes, sir.
Hello.
Yes, sir.
Just to conclude, I would like to thank all the enthusiastic signal engineers of the world. In fact, many of the people are from Vietnam and from Israel and from other countries. So I would like to thank all of them for the interest they are showing on this very complex area of work, but it is a very interesting work, very innovative work. And that is what is gladdening, that we, all of us, are into this area. I would like to thank Mr. Ajay Singh and Mr. Parvatikar, who have been the pillars of strength, because I really I admire their commitment, Mr. Ajay Singh and Mr. Parvatikar. Thank you so much, and thank you so much for Mr. Kanu.
Thank you, sir. Thank you, sir.
And Mansukani, wonderful. Well, let us see you again.
Thank you, everyone. Have a nice evening ahead. Good night.
Good night.